Hi class, we're starting a new chapter today. This is chapter 8 and it is about gases. We're going to get more involved in the nature and behavior of gases and pressures and how pressures affect gases and so forth. Here is a patient that has an oxygen tank to help him with his COPD. So let's take a look at the kinetic molecular theory. Now kinetic means movement and molecular is molecules. So this is movement of molecules theory, but it's also atoms and so forth. A gas consists of small particles that move randomly with high velocity, high speeds. 2, have very small attractive or repulsive forces between each other. So this theory has summed up the behaviors that they have determined from what they call small particles, which is molecules. Occupy a much larger volume than the volume of molecules. I'm going to break all of these down. Are in constant motion, moving rapidly in straight lines, have a Kelvin temperature proportionate to the average kinetic energy of the molecules. So the first one is that molecules move very, very quickly at a very intense speed. They are always in motion. And if you jump down to number 4, they are moving in straight lines, unless they crash into another molecule or when they hit the boundary, usually a wall or container. Then they pretty much just repel and start back up into the other direction. Constantly moving, do not stop moving unless they are forced to stop by an impact, and then they start up again. They have very small attractive or repulsive forces. Because they're going so fast, there's not enough time for them to interact with each other. And in reality, they do actually have some attractive forces and repulsive forces. But in this chemistry, we're not going to deal with that. So you're lucky. We're just going to ignore that because it's such a small, minor amount anyways, that we're going to pretend that they absolutely have none. They want nothing to do with each other. And they occupy a much larger volume than the volume of molecules itself. A perfect example of this is perfume. Have any of you ever smelled somebody walking in with strong perfume? It will carry to you even if you're in the furthest part of that room. That's perfume is because of perfume molecules. They will take up the whole room and they won't stop until they hit a boundary. So that's what it means, that even though the molecules are very, very tiny, they will occupy as much space as they're given until they're forced to stop or contained. And then Kelvin temperature has to do with the average kinetic energy of the molecule. So they take an average of all the speeds of molecules in, let's say, a container. Now, average means that there's some going faster and some going smaller. They take the average of that. And what they found, that the speed of the molecules is affected by the temperature. So let's talk about a tire. If you have a bike, and let's say you look at it in the morning, your tire may look flat, but there is air in there. What happens is if you get home from school and then you notice in the daytime it's maybe 90 degrees, now your tire for your bike does not look flat anymore. That's because the temperature in the morning is lower, so the speed of the molecules, the air molecules in that bike, are going at a much slower speed. So they're not pushing against that container, because every time these molecules hit a container, there's pressure there. But as the temperature starts rising, these molecules get more and more active and they start moving faster and faster. So the higher the temperature, the faster the molecules will go. Okay, so gases are described in 4 properties. There's pressure, volume, temperature, and amount. Pressure is the force exerted by a gas against the walls of a container. So the walls will keep hitting that container because they're constantly in motion until they hit another obstacles in this case, and it will go the opposite direction. But it'll constantly stay in motion. So it'll just keep hitting, and there's a buildup of pressure inside this container. Think of a soda. Once you open the soda, the gas releases from it. But up until that point, there is pressure inside that soda can. Now, the units of measurement are atmosphere, millimeter mercury, which is mmHg. This is mercury, torr, and Pascal. There's also inches mercury, so it would be inches in mercury. I don't know why that one's not listed here. Volume is the space occupied by gas, and it's usually in liters or milliliters. Temperature, we tend to use Kelvin more than Celsius, but it can be in Celsius here. But mostly when we deal with gases, we're going to deal with Kelvin. And N is the amount, the mole, the quantity of gas in a container. You can be given gram, or mole. And if you're giving gram, most likely you'll have to move it to mole and so forth. So I found this little depiction, but these balls here are actually going really, really slow compared to what it would be. It would just be crazy fast. Excuse me. The volume of a gas is the same as the volume of the container it occupies. So we don't compress this and say, okay, we're going to try to keep them right, next to each other, touching, and figure it out. Whatever the volume of the gas, the container is, that is the volume of the gas, because the gas will keep expanding until it cannot. It's usually in liters or milliliters. It increases with increasing temperature. So if you keep, let's say we have a constant pressure, and I know I haven't covered pressure yet, but let's say we keep this at constant pressure, room pressure, temperature, room pressure, which you may not understand what that means yet, but let's just pretend for a second there's a number that goes with that. Now, in order for, if we increase the temperature in this box, it's going to increase the pressure, because these molecules are going to speed up even faster and faster, and every time they hit the wall, they increase the pressure. So in order for this to not happen, we have to, if we want to keep it at constant pressure, we have to change the volume of this box so that we can adjust for the temperature going up, but we expand the area out so the gases have more room to move and less chances of coming together, which also causes pressure, and hitting the boundaries, which causes pressure. So we adjust one other variable in order to keep the pressure going at the same pressure it was when we started keeping temperature. Don't worry, if that doesn't make sense, it will in a few other sections. So here's a picture. I tried to find a GIF that matches it, but it really needs to show a lot faster. And the red ones are different gases than the blue ones, is what that's showing. Okay, so temperature. The temperature of a gas relates to the average kinetic energy of the molecules and is measured in Kelvin. So we tend to use Kelvin. You might be given to you in Celsius. You'll just have to change it to Kelvin. When the temperature of a gas is decreased, the molecules have fewer collisions because they're not going as fast. So they're moving slower. They are not being just moving slower. They're not coming into contact as fast or with the same amount of intensity. As the temperature increases, now they're moving frantically, which means that they have more chances of having collisions, which increases the pressure. So now let's talk about pressure. We really don't pay attention to pressure because of the fact that we were born with pressure around us. It's always here. The only time that you're aware of pressure and pressure differences is if you're in an airplane or you're sick and your ears won't pop. That's when you start realizing that there's actually pressure. And because there's constant molecules bombarding our bodies, we're so used to what the atmosphere is that we don't pay attention. You're not aware of it. We have pressure on the inside that keeps us from collapsing inside from the outside pressure, and we have pressure on the outside. So we have pressures on both that keeps us going. We just don't pay attention until you try to pop your ears and you can't. Pressure is a measure of the gas particle collisions with sides of a container, and it's measured in units of millimeters. So I already went over this. I'm going to explain what this means. So our air, we have in our environment, we have different molecules of air. We have our air is actually made up of 78% nitrogen. I know everybody talks about oxygen, but we have more nitrogen in our air than we do oxygen. We have 21% oxygen in our air. And then the last remainder of 1% is water vapor. It's other gases. And depending on where you are, the water vapor will be different. Say if you're in Vegas, the water vapor there is a lot different than something that might be Seattle. So there's a little bit of differences. But the pressure on this, that's what's called the atmospheric pressure. So I found... Let me go to this picture. Well, I'll start here. Okay, so how do we know what the atmospheric pressure is? I'm going to explain that a little bit more. I found a little cartoon to explain about atmospheric pressure. So we can determine what atmospheric pressure is by using a barometer. This barometer is filled with mercury, and it looks strange, but it actually does a good job. And this thing was discovered, I think maybe 1700s or 1400s, a very, very long time ago. So it measures the pressure exerted by the gases in the atmosphere, indicates atmospheric pressure as the height in millimeters of the mercury. This is a typo. There should be no space there. It Should be like this. So let me explain how this is. This is a container. This part is open, so it's like an open dish. But inside, this glass is open at the bottom. So this mercury can go up this tube, and it's a vacuum, so there's no air in here. The air has been completely removed inside here. Now, what happens is that at 1 ATM, 1 atmosphere, which is sea level, this is marked. They have it marked somewhere here on here. There's markings. Now, if the atmosphere intensifies, so if it goes above 1 ATM for the day, then what happens is that the pressure on the outside will push down on this, and in order to relieve that, this will push back up. So this will go up, and they have markings so they can check what it is. Now, let's say that the atmosphere for that day is, it's a cool day, maybe it just rained and so forth. The atmosphere is below 1 ATM. What it'll do is that there's not so much pressure on this liquid on the outside, and this will relieve the pressure that's being forced down, and the pressure will come up, and that will lower this part of it. So it will indicate to here. So let me repeat this. If the pressure is really high for a day, the pressure will push down on this and forcing this column to go up, the mercury in here. And there's I can't think of the word. There's markings on it, so they know. And if the pressure is not strong for that day, this arrow will go away, or it will be a smaller arrow, and this liquid will fill up more in the jar, and this will actually go down. Okay, so that's how they are able to, they know atmospheric pressure by the differences in this container of mercury. So here are some more units. There's atmospheres, ATM, 1 ATM. These are all exact. These ones here. Millimeters of mercury is equal 760 millimeters mercury. Torr is 760 torr, so these are the same, which is nice. Inches of mercury is 29.9 inches of mercury. This one, remember, we also have millimeters mercury, so it's actually what we understand, inches and millimeters. And pounds per square inch, PSI, is pounds over square inch, inches squared. Pascal, very large number, and a kilopascal is still large, but not as large. Okay, so let me explain a little bit more about atmospheric pressure. So atmospheric pressure at sea level is 1.0. But as you start going up, 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 you know, they say the air is thinner up there. So I'm going to explain what that means. So if you go up, now the pressure is 0.70. What's happening here? Well, if we look at it as a column of air, so if we take a spot or a chunk out of Earth and we place it like, imagine a column just placed over any part of this. And then what they do is they measure, I don't know how they do this, but they know how to do this. They can determine how many molecules are at what altitude. So the atmospheric pressure is the pressure exerted by a column of air from the top of the atmosphere to the surface of the Earth. It decreases as you go up, which shows in these numbers. So it's really strong here, and then as you go up, it goes up. That's because the air gets thinner. So I found a nice little cartoon to show you what I mean. So here is, I changed the guys on here. I didn't like what they look like. So I found this, somebody else also must have had the same feeling about what they had put here. So I changed them out, and somebody else did too, but I didn't like their other thing. So let me explain this. At sea level, we have tons of molecules on us. They're bombarding us constantly, but we don't feel it. Now, as you start going up, the air gets thinner and thinner, which means there's not as much air up there, not as much, oxygen to breathe and so forth. That's what they mean by the air being thinner. There is less molecules as you go up, so there's lower pressure up here. So there's less molecules bombarding the sky than there are up here, down here. This is what high pressure means. This is what low pressure means. Is the molecules hitting you constantly are lower up above. So the lower pressure is the molecules are not hitting each other as much. So there's lower pressure. And down here, constant molecules are colliding with stuff, so the pressure is very high. Okay, so altitude and atmospheric pressure. It's exactly what I had just kind of showed you here. On a hot day, the mercury column rises, which is, here's a little picture to remind you, it will go up because the pressure will push down on this, indicating a high atmospheric pressure. On a rainy day, the atmosphere exerts less pressure. So let's see, pretend we pull this arrow up and now allow this liquid to come here, and it will push down on here because it can release the pressure that's inside the column. So at altitude, you can see atmospheric pressure at the Dead Sea is 800. Sea level is 760, which is 1 atm. Los Angeles is 752. Las Vegas is 700. So you can see the altitudes based on, the altitude, you can see where things stand compared to the atmospheric pressure. So the Dead Sea is below sea level. So that means there's even more intense pressure there that it's more than 1 atm. Excuse me. Sorry about that. I'm still a little sick. I kept trying to pause this and it wasn't pausing, so you wouldn't hear me cough. Okay, so you can see the Dead Sea is actually below sea level because of sea level is 760. The atmospheric pressure is increasing. So if you think this is sea level, you go down more, you can just imagine even more molecules are bombarding you at below sea level. Okay, so hopefully that makes sense on here. So let's understand conversions now. What is 475 millimeters mercury expressed in atm? So all we're doing is we're taking the conversions that I showed you, and we're going to start jumping between these so you understand how to convert. Okay, so if we have 1 atm equals 760 millimeters mercury, we just set that up. We set it up with what we're trying to get rid of and what we want. So if it's, oh, I apologize, this skipped too. I try to go through these. I don't know why I use Chrome. I use Google Slides, and then I transfer it over to Windows and PowerPoint, and sometimes it messes stuff up and I don't catch it all the time. I don't know why it does that. So here is, so we cancel out mercuries, we have ATM. So this answer is B. So if we looked at all these answers, the answer is going to be B. So the conversions here are not very difficult. You just have to know the conversions, and most of them will be given to you, and you're at home anyway, so you could access what you would need. The pressure in the tire is 2 atm. What is the pressure in mercury, millimeters mercury? So now we're going the other way. So now we set it up the same way, but using the opposite units. What we want to get now, we want millimeters mercury. So we are going to, and this is exact, so we don't have to worry about that. So this is 3 sig figs, the answer is B. Okay, the downward pressure on the mercury in a barometer is blank the pressure of the atmosphere. So is this greater than, less than, the same as? This is to understand atmospheric pressure, meaning the pressure on the atmosphere. So it should be the same. If it's not the same, then it's not really helping us. It's like a thermometer. If it's not giving us the temperature, it's giving us an approximate, then what's the point of it? So it should match the same, because how we're reading this is reflective on the actual atmosphere. So it's C, and I jumped on this one, but let me explain it anyways. A water barometer, so it's the same as this, but it's instead of mercury, it's water. Now, it's taller than a mercury barometer. Density of mercury is 13.6 because, so why is it taller? Water is less dense than mercury. Water is heavier than mercury. Air is more dense than water. Water density is 1.0. So there's a huge difference from these. This is very simple. Since we don't want to touch mercury, think of a brick. A brick would have a very high value of density, and water is like styrofoam. So you would have the same amount of styrofoam and brick, but the brick's going to have a way more larger value of density, which means it's going to be very small and impacted because all those atoms are put together. So in this case, density of water is far less than the density of mercury, so it's got to be a lot bigger because you think of styrofoam. It's not as scrunched together or compressed the way a brick or apparently mercury is. So the answer is A. It's less dense. And that's it. Thank you.